Welcome, Pre-Calc. Let's take a look at Chapter 7, Section 3, plotting points in three-dimensional space. No longer flat, but now we add a length, a width, and a height, so you get 3D shapes. Using back substitution and Gaussian elimination to solve systems in 3 variables. So, you're used to having an XY plane, and that's still there. We have rotated things around a little bit though. So you're used to X being here, Y being here. Well, that's now laying flat. It's like taking your XY plane that would normally look that way on paper, but turning it this way. All right, so we've rotated a little bit to accommodate the Z axis, which represents height. So think of the X as coming out at you. This would be your positive X. Back here behind this plane would be the negative X. To the right would be your positive Y. To the left over here of this plane, the green one, would be your negative Y. And then your vertical axis would be represented by the blue. You've got your positive Z, and below that would be like below the floor, it'd be your negative Z axis. So if we take a look at plotting some points in three-dimensional space, sometimes what we use is isometric paper, where it has a bunch of little spaces in it that we can fill in, and we can try and graph these. All right, so we'll start with just a few points. And what I want to do is I want to take each of these. You'll notice the X and the Y are the same. The Z value is changing. And I want to do that in math3d.org's website so we can see what's happening. If I try and graph 2, 3, 0, well, keep in mind, this is your x-axis. Over here is going to be our y-axis. This is going to be our z-axis. So if I go 2 units on the x positive and 1, 2, 3 units on the y, and I don't go up or down at all, well, that's where I am. But then as soon as I add that z component, where I'm now going 2 units out, 3 units over on the y, and 1 unit down, well, it takes that point and it moves it down 1. Or maybe if I go down 2. Or down 3, down 4. So it's going to be around there somewhere. Let's take a look at it on Math3D. And that's a website that you can always pull up on your Chromebook and take a look at too. So Math3D, they like to start you off with a fancy shape on here. They call it an explicit surface. It's a 3D shape. I'm just going to X out of that, clear my axes. And you'll notice right now, they've got the X over here, the Y here, the Z here. So if I click and I kind of rotate it the way that we're seeing it, now you see the positive X's, the positive Y's, the positive Z's. My next step would be to add an object. Looking to add a point. Hopefully you get my point. We'll start with 2, 3, and 0. There it is. We went out 2 over 3. We didn't go up or down any. But as soon as I go down 1 point, or down 2 points, or down 3 points, or down 4 points, you'll see my point is moving. And it becomes very difficult then to visualize that this was still 2 units out and 3 units to the right. But it just went down from there. So sometimes what you'll see is people will actually trace it out. They will draw a little line out to here, draw a little line over to here to 3, and then they will draw the line down to trace it. If you get really good at this, you tend to draw a lot of boxes, a lot of rectangular prisms that represent that movement that you're seeing. So let's try another one. -1, -3, and 2. Keeping in mind, this is our X, This is our y. This is our z. So we're going to go left one. No, remember, x doesn't go this way anymore. How does x go? Oh yeah, out towards you, or negative would be back. So we're going here. Then we're going to -3 on the y. So 1, 2, -3. And you can see 1, 2, 3. So we were back 1 to -3. That's right here. Now we need to take that and raise it 2 units up. So taking that point, going 1, 2 units up would put us about there. 3D space gets fun. How about you give it a shot? Let me draw that one on Math 3D. And then when you're done trying yours, you can try your point that you graph on Math 3D also. So I'm going to go to math3d.org, clear out my explicit surface, rotate as needed so I can see what's going on, and add my point. That point was -1, -3, and 2. So the cool thing about this is I can rotate it and I can see what's happening. I can kind of go this way a little bit and I can see how it's doing. I can go this way. So we get the benefit of some perspective here. Sometimes you'll see your X, Y, Z axes like this. Sometimes you'll see them like, how else would they do it? They might do it like that. It just depends on the book you're using. It really, there isn't a right or wrong way to have it because this is 3-dimensional space. And in space, there really is no up or down, so to speak of. There is no left or right. It's just space, the final frontier. So, how about you try? Try to plot those 2 points. When you're done, maybe, just maybe, you can try it on math3d.org. I do have some 3D graph paper for you to try this on. So use your isometric graph paper, try and plot them out. Pause for a minute. When you're ready, come on back. All right, let me see if I can graph 1, 4, and 0. So x is 1, forward the 1, y is 4, 1, 2, 3, 4, and then z doesn't move up or down, it's 0. So it's around there. Next one, 3, -1 and 3. So coming 1, 2, 3 units here, going left 1 unit to the -y. This would be your -1, this would be -2, -3, and so forth. So 1, 2, 3 over here, and then up 3. 1, 2, 3. Puts me somewhere in here. You're like, wait a minute. No, these lines are for the y. That's where it gets tricky. If we do it on math3d.org, we'll hopefully see what's going on. Let me add another point. One, 4, 0. I'm going to adjust my XY axes to my liking. There we are. We went forward 1. We went 1, 2, 3, 4 units over. Add another point. Three, -1, 3. So went forward to 3, over 1, and then moved up 3 units. And you can kind of see now in space, some of the points are higher, some of them are lower, right? This point is up at 3, this one's at 2, this one's sitting on the XY plane at 0. So the perspective makes it challenging at times to see. Okay. And if you get good enough, you can play around with it. Sometimes what helps is going to your axes and camera and turning on the thing that says use orthographic projection, so it doesn't give as much perspective that way, and maybe it's easier for you to visualize it then. This looks more like it's at 2, this looks more like it's at 3, that looks more like it's at Y, not Y, the Z-axis is 0. If we were to look straight down on it, we'd see for this point we went down 1, 4 to the right. This one we went left 3, up 1, it looks like. And this one looks like we went 1 left and 3 down. So play around with it, try and visualize it, and see what things happen. So here's a little video that's going to show us how to draw in 3D space. I am not an artist, but it's about following the correct lines. So they're going to try and guide us. After we get a commercial, because who doesn't love a commercial? Thank you, YouTube, the highlight of our day.
Hi, this is Ms. Cooper with a tutorial on the beginner basics of isometric drawing. Now, isometric drawing is when you take shapes and make them 3D, but you do it on paper that has a triangular grid. This is great because it gives you some rules when you draw so that you can do things out of your imagination and figure out a basic structure. Now, when you first grab your sheet of triangle gridded paper, because you do need this kind of grid to work off of, make sure that your lines are going vertically because you will need these. When you draw, your lines have to go up and down, and they can also go to the side to show some kind of depth, and this can also show the front of your object. So let's start with a basic cube. Let's say you are trying to draw a square, but you want to make that into a 3D cube. Well, first I'll show you a don't of isometric drawing. This is a don't. This does not follow the lines. Yes, it does have the vertical lines, but it has horizontal lines, and these are a no. We don't do horizontal. That is not part of isometric drawing. We do use verticals, and I'll show you how you do the sideways parts of the cube. So let's say our cube is a couple triangles tall. When you want to show that it goes back in space and to show the front side, you rotate it so that it goes along the grid. So this one is 1, 2, 3 triangles tall. So let's make it 1, 2, 3 triangles wide. This shows the bottom of my front side. Now let's complete the front side. So it's 3 triangles tall, so the other side will also be 3 triangles tall. So we will draw that line, and we can complete the front side by drawing the top. So that square shape has now become a rhombus because when we see something that's rotated away from us, it takes on more of that type of shape. Now let's say this cube isn't a perfect cube. Maybe it's actually a square prism and it just goes backwards into space a little bit. Let's take it back 2 triangles. So it is that deep. That means that we can now complete the height. It's again, still 3 triangles tall. So we will draw from top to bottom on our vertical lines and complete the side. Now the last part is completing the top of our square prism. We can kind of see where the lines are going to crisscross, but if you don't remember, it's 2 deep and then it is 3 wide. So now we've completed our square prism. So let's label the parts in case you need a little reminder breakdown as we go. So this is the front right here. We will call this side the front. We'll call this the depth. This is how deep it is, how far back it goes into space. And then this right here is the very top. You could also call this the side, I suppose, as well. So some things that we don't do, again, we don't do horizontal lines. This doesn't make sense on an isometric grid if we draw our cube going back into space. The whole point of these lines is that it gives us some rules, and this will get very confusing later on down the road. You also have to be careful of how you draw things. So let's say we did the front correctly, it's all 3 cubes wide, it all makes sense, but we're trying to make it 3D. Well, if you extend it downwards, that becomes wrong, that becomes an issue. We don't have space here all of a sudden. Or if you just kind of don't measure far enough and you just kind of draw your lines, well, now the top has become slanted, and unless that's what you were going for, that might be a little confusing to the person viewing it. It might be hard for them to understand what's going on. So just make sure that you count very carefully how wide everything is as you go, and perhaps do it in pencil if you're not feeling entirely confident. I'm doing it in Sharpie so you can see really well in the video. All right, so now you know some of the absolute basics. In my next video, I'll talk about how to do some slightly more complicated shapes and how to include a hole in your piece. So thank you for watching. Please add questions down below if you have any. Thank you.
You're welcome. I'd ask if you have any questions, but I'm not here, sorry. See you next time. Groups, how about you spend a few minutes trying to do a little graphing in 3D space, have some fun with it. If you take calculus, let's see, my first dabbling in 3D drawing was in Calc 3 in college, so something to look forward to. The other thing we're going to do today is solve systems of linear equations. We've got 1, 2, 3 variables, we've got 3 equations. So how would you solve an equation system like this? You might have some ideas, but they're complicated. They take time. So one technique that we can use is called Gaussian elimination. It's named after Friedrich Gauss. He is a brilliant mathematician. You can look up Mr. Gauss. And what he came up with was being able to convert the system into an equivalent system called row echelon form. Row echelon form, what it does is it follows a stair-step pattern. So we have stair steps where the leading coefficients turn out to be all equal to 1. And that's how our system eventually looks when we're done solving it. We have x plus everything else equals a number. X is gone. Now we have y plus everything else equals a number. X and y are gone. We just have z equals. So it's kind of like a stair-step pattern. Gaussian elimination. We keep eliminating variables until we're able to solve the equation. We'll do a quick little brain break, then we'll take a look at how to solve it. Evaluating algebraic expressions and solving linear equations sounds like fun, said no one ever. Can you solve it? The number of towers, the number of candles, the number of sheep. That's easy. The answer is, well, you pause for a minute and see if you can solve it. All right, so we have sheep plus sheep plus sheep equals 45. We have sheep plus tower equals 21. We have tower plus candles equals 7. We have candles plus sheep plus tower equals question mark. Looks like we've got 2 towers here, 3 candles here, 4 candles here, 3 towers, 3 towers, 3 towers. So pause it, see if you can come up with a solution. You should definitely at least be able to get your number of sheep. I know, this is pretty bad, but you can do it. All right, so this says, that's easy. The answer is 20. how many towers, sheep, candles, right? Right. Oh no, math! Ew! Right? People don't mind doing this stuff, but you give them this and they start freaking out. We had 1 sheep plus 1 sheep plus 1 sheep equals 45. I'm hoping you got 15 for a sheep. Yes. Then we have 1 sheep plus 3 towers equals 21. So you can plug in your 15 here, subtract from 21, leave you 6y equals 6. Y is 1. Then you got 3 towers plus 4 candles equals 7. So 3 times 1 is 3 plus 4z. Take away 3, so 4z equals 4. Z is also 1. So your candles plus your sheep plus your 2 towers. Let's see. 3 times 1 would be 3 plus 15 up to 18 plus 2 times 1 would be 20. Oh no, math! So how do we do this whole Gaussian elimination? Well, we use what are known as elementary row operations. These are the things you're allowed to do to be able to solve the equation. The first thing is you can take 2 equations and you can interchange them. You can take row 1 and flip it with row 2. You can multiply one equation by a non-zero constant. So you can't just multiply everything by 0. But it could be any constant, whether it's a whole number or even a fraction or a decimal. Positive or negative even. And we're allowed to add a multiple of one equation to another. So I could take twice row 2 and add it to row 3. That's allowable. Right? So those are the 3 things we're allowed to do. Here's our set of equations. Let's see if we can go ahead and try and solve this using Gaussian elimination. The goal is to keep eliminating our variables. We want to get that stair-step pattern. So I'm trying to turn this first equation into something I can work with. I'm trying to turn that second equation into something I can work with. And when I say that, I need just x in that first equation and then everything else. Well, I have that already. I have 1x. I have just x. So that first equation is really good to go. Let's focus on our second equation. The problem is it has a negative 1x. That can't be there. It has a 3 in front of the y. That can't be there. So my first step is I'm going to eliminate that x. How can I do it? Well, I'm allowed to switch rows. I'm allowed to multiply a row by a non-zero constant, or I'm allowed to add multiples of one row to another. And if I look at the first row and the second row, and I'm thinking, if I add these together, if I take row 1 plus row 2, then here's what I'll get. The first row stays the same. Third row is going to stay the same. But that second row is going to change. So when I add these together, I'm replacing the second row with that new sum. So let's add them together. Row 1 plus row 2. X and negative x make 0. They're gone. That's good. That's what we want. Negative 2y plus 3y. Well, that would give me y. 3z plus 1z would be 4z. And negative 9 and negative 2 make negative 11. So we're building that stair step. Next up, let's see. I've got x all by itself. X is gone. I got y all by itself. I guess my next step is I need to get rid of x and get rid of y and just have z equals a number. So, how can I eliminate this x? Well, I could multiply by -2 and add it to here. So, negative, writing it in the wrong spot. -2 times r1 plus r3. First row stays the same, second row stays the same. Third row is changing dramatically. Let's take -2 times x, add it to 2x. -2 times x would be -2x, plus 2x would make 0. X's are now gone in row 3. -2y times -2 would be 4y, and -5y. 4y minus 5y would leave me -y. -2 times 3z would be -6z plus 5z would give me -z. -2 times -9 would be 18 plus 17 would give me 35. Well, we've eliminated the x from row 3, but we still have the y. So what could we do to get rid of this y here and just leave us with our z? Well, we could add row 2 and row 3. Let's do that. Row 2 plus row 3. First two rows will stay the same. X minus 2y plus 3z equals -9. Y plus 4z equals -11. Now adding row 2 and row 3. Y minus y would be 0. Awesome. Those are gone. 4z minus 1z would leave me 3z. -11 plus 35 would be 24. We almost have it. We need to get z, not 3z. So we are allowed to multiply by a non-zero constant. What could we multiply 3 by to get rid of it? Yeah, 1/3. Right? So 1/3 row 3 will give us our set of equations. First row stays the same. X minus 2y plus 3z equals -9. Y plus 4z equals -11. 1/3 times 3z would be z. 1/3 times 24 would be 8. Guess what you just found? Z is 8. So as we're looking for our solution, we just found z is 8. We still have to find x and y. How can we find x and y? It's called back substitution. You take your 8, now we plug it into this equation, the one right before it. Once we do that, we'll have an answer for y. So let's plug it in. Y is going to be, not y equals, jumping ahead, I gotta show my work. Y plus 4 times 8 equals -11. So y plus 32 is -11. Minus 32 on each side, y is -43. We still have to find x. Well, you have y and you have z, so let's go back to our first equation here. X minus 2 times -43, that's y, plus 3 times 8 is z, equals -9. Running out of room here. I need bigger whiteboards. X plus 86 plus 24 equals -9. Let's see. 86 and 24 would be... Here I am jumping to the answer again. Sorry. X plus 110 equals -9. Subtract 110 on each side. I got negative 119. There's our solution. Negative 119 for x, negative 43 for y, 8 for z. What you're getting is these three linear systems here, this linear system, they all intersect at one point. Graphically, it would look like this first one. We're intersecting at one point. Our solution is x, y, z. We have three different planes of existence, and they are intersecting at one point. In the second example, you've got three different planes. Well, 2 and 3 are sitting on top of each other. So it's really only looking like two planes that are intersecting, and this intersects as one line. That line going right here. Every point on that line is a solution. So you really have an infinite number of solutions because it's an entire line, and lines go on forever. This next example, we have three planes that don't intersect, don't touch at all. So how many solutions do you think we have? That's right, they don't intersect. There are no solutions. Or if we have two planes going this way and a third one cuts across this way, well, they're never all three going to intersect because these two planes are parallel. That third one's crossing through, so again, there's no solution. Or maybe they intersect and form a little triangle in the middle. Guess what? All three planes are not intersecting, therefore, no solution. Or maybe we've got one plane here, and parallel to it are planes 2 and 3 that are sitting on top of each other. Well, all three planes will not intersect. No solution. How about here? What do you think? Well, 1 goes this way, 2 goes that way, 3 goes that way, and they all intersect right here. So your solution is one line again. You have an infinite number of points where they intersect. Our final possibility would be, what if all the planes are sitting on top of each other? Well, then what you really have is just one plane. And one plane has an infinite number of solutions. It's every point anywhere. You'll deal fun with that with calculus in college. You'll like it. Or not. I don't know. But I know you're going to love this. Chapter 7.3, Systems of Equations. Have fun with that. And check to see if you have online homework. Have a good night. Bye, guys.